vehicles are called autonomous vehicles. Examples of autonomous vehicles are robots, driverless electric car, unmanned aerial vehicles like drones, missiles, etc. But these are the some of the examples of autonomous vehicles. And in today's session, I will be concentrating on the missiles. Also, we know the dynamics of these vehicles are highly nonlinear, and so designing a controller is a challenging task. Now, we know the safety and security of people, land, and other properties are utmost important for any country. It is the primary duty of any government that there should be some mechanism for destroying enemy weapons and their destructive equipments or such vehicles. For this, to achieve this, we know missiles can be used because they are very important role to achieve these two objectives. A flight vehicle, it can be a missile or aircraft or launch vehicle, requires the help of human intelligence to achieve their mission. For such human intelligence, getting such human intelligence is known as guidance and control. Now, the objective of this today's presentation is to understand the basic concepts and principles of guidance and control, to learn the classical guidance law, to understand the development of mathematical models of missile target engagements. Also, we may discuss guidance law for controlling the impact time and impact angle. But I think we have a constraint on the time, that is this session is only for 1.5 hours. So if we get time, then we will discuss this control aspect also. Otherwise, we will stop after discussing the other three objectives. Now, first we can have an introduction to guidance law. I think many of you may not be having an awareness about the guidance law, or this may be new to you. Therefore, before going to the control aspect, I think it is good to explain the guidance law. Now we can consider here a missile target engagement. Here, this is the initial position of the missile, and this is the initial position of the target. We assume that the target is not maneuvering, that is, the target is moving along a given direction, a particular direction. Therefore, the target is moving along this direction. Initially, the missile was here. The objective is that the missile should hit the target. Therefore, the missile has to maneuver, or it should turn its flight such that finally it will reach the predicted interception point. Now, for the determination of flight path, we have to determine a flight path and associate control histories for a given flight vehicle to achieve a desired objective with a specific constraints is known as flight path planning. Therefore, first we have to plan a path so that the interception of the missile with the target will be achieved. Now, in order to achieve this objective, the vehicle should know its position, and also should know the position along the path, and also the position of the target. All this can be get or obtained from its sensors, and this is called a navigation. Now we have to determine a methodology by which the vehicle can follow the normal path. Now, this is suppose this is a normal path. Then we have to develop a methodology by which the vehicle, that is missile, is able to move along this path, or it is following this path. That methodology, that strategy is known as guidance. And also, in order to achieve this one, we have to make sure that the orientation, the angular orientation, is along a particular direction, and for that a control is required. But this is some basic concept about the navigation, guidance, and control. Okay. Based on the information gathered from the environment, if an object moves such that it comes closer and closer to stationary or moving target, the target can be either stationary or moving. So based on the information that we have, the vehicle has gathered from its environment, if the object is able to move closer and closer to that point, then we can say that the object is guiding itself towards its goal point. A guided missile, an unmanned vehicle which carries within itself the means for controlling its flight path is known as guided missile. Now, we can have some basic concepts on interception and avoidance. In the case of missile, the primary objective is interception. That is, the missile should hit the target. But whereas in the case of robots, the main objective may be to avoid an obstacle. Therefore, these two things are actually two sides of the same coin. Therefore, if we have a strategy that can be used for intercepting a target by a missile, then the opposite strategy can be used to avoid an obstacle by a robot. Now, we will discuss the engagement between 2-point objects. But here we assume that we are not applying any guidance law. If we are not applying any guidance law, what is the condition so that a missile will hit the target? If we know that condition, then what we can do? We can develop a methodology such that this condition is satisfied. Once this condition is satisfied, we can ensure that the missile hits the target. Therefore, first we will consider a case where the missile is not guided, unguided missile. So here we have a missile M and a target T. This is the directional velocity of the missile, and this is the directional movement of the target. Okay, we assume that there is no maneuvering. Now we have some definitions. The distance between the missile and target is known as line of sight. It is usually denoted by the letter R, which is also known as range or LOS separation, the line of sight separation. And the angle made by this LOS with respect to a reference, for example, x-axis, is known as LOS angle, and it is in this presentation it is denoted by theta. And the angle made by the velocity vector of the missile with respect to a reference axis is denoted by gamma. It is the flight path angle. Similarly, similar definition we can have for the target also. So once again, here we are not guiding the missile. Our objective is to see that what is the condition that must be satisfied so that this missile will hit the target. Now we can think about the modeling of the kinematics or the modeling of the engagement between this missile and target. What we are doing is that this velocity vector of the missile is resolved into two components. One component is along the direction of the LOS, and the other component is perpendicular to LOS. The same way, we have resolved the target velocity also as two components, one along the direction of the LOS and the other along a direction which is perpendicular to LOS. Therefore, this component VMR is the component of the missile velocity along the LOS that can be obtained as Vm into cosine of this angle. But this angle is actually gamma m minus theta. Therefore, we will be getting VMR is equal to Vm cos gamma m minus theta. Similarly, we can get the other component Vm theta is equal to Vm sin gamma m minus theta. In the same way, we can resolve target velocity as two components as given by these two equations. But here we assume that Vm, Vt, gamma m and gamma t all are constants. Therefore, the only state variables are r and theta. Therefore, in order to develop a mathematical model, we have to find r dot and theta dot. So r dot is the velocity along this direction. That is r dot. But dr by dt, that is the velocity along this direction. But that is nothing but the this velocity, target velocity minus this missile velocity components. Therefore, Vtr minus Vmr is the velocity along this direction. Therefore, r dot will be equal to this expression, equation 1. In the same way, V theta, that is also equal to r into theta dot, that will be equal to the difference of the velocities along the direction perpendicular to LOS. Therefore, this velocity component minus this velocity component will give you r theta dot. Therefore, these are the two state equations or engagement equations for this case. Now, using these two equations, we can develop a methodology so that we can derive the condition for capturability of the two vehicle, the missile and the target. So for that, first we will obtain a V theta VR trajectory. V theta is the velocity along the along a direction perpendicular to LOS, that is theta dot, and VR is R dot, that is the velocity along the LOS direction. So we can get many interesting results if you draw this V theta VR curve. Okay. For that, what we are doing is that first we will find VR dot. That is, we will take the derivative of this equation, VR dot or R double dot. If you differentiate this one with respect to time, then we will be getting Vt sine gamma t minus theta into minus theta dot. Similarly here, Vm cos gamma minus theta into minus theta dot. Therefore, we will be getting an expression like this one, which can be simplified into theta dot into V theta, because Vt sin gamma t minus theta minus Vm sin gamma minus theta is, we have already defined or obtained as V theta. Therefore, we will be getting an equation like this one. Similarly, we can obtain the other equation, V theta dot is equal to minus theta dot into Vr. Now, in both expression, we have theta dot. Therefore, from here, theta dot is equal to Vr dot by V theta. And from this equation, theta dot is equal to minus V theta dot by Vr. We have got this equation. Now, we can cross multiply these two equations. Then Vr dot is equal to minus V theta dot, or Vr dot plus V theta dot is equal to 0. We will be getting an equation like this one. Now we can integrate both sides, and we will be getting Vr square plus V theta square is equal to C square. It is clear that it's obvious that this is the equation 9 represent that of a circle with a radius C. How we can get C? By substituting the initial condition, we can get the value of C, which is obtained as this by this equation. Okay, therefore the trajectory Vr V theta will be a circle of radius square root of Vr naught square plus V theta naught square. Multiply equation 4 and 6 by R yields. That is, what we have to do is this equation 4, this equation and this equation, these two equations are multiplied by R. So R theta dot V theta minus R theta dot Vr. Here also R and R will be coming. Therefore, we will be getting R Vr dot is equal to R Vr dot is equal to R theta dot into V theta. But R theta dot by definition it is V theta. Therefore, V theta into V theta is V theta square. Therefore, we will be getting an expression like this. And similarly, R V theta dot will be equal to minus V theta Vr. So from this, we have already seen that the trajectory of this Vr V theta is a circle. Now we have to see what will be the direction of the trajectory as the engagement proceeds from t equal to 0 to t equal to infinity. But that can be obtained from these relations. From here, it is clear that Vr dot should be positive, because V theta square is always positive. Therefore, Vr dot should be positive. Therefore, Vr is increasing. From here, we can see that if V theta and Vr are of the same sign, then this will be negative. And if they are opposite sign, then this will be positive. Therefore, based on these three informations, that is from equation 9 and from this and from these two, we can draw the Vr V theta trajectory. Okay. But this is the trajectory Vr V theta. But here we can see that if you draw like this, if the arrow mark is like this one, then it means that as time increases, your Vr is increasing, because here this is the Vr, and for this time this Vr, it is anyway increasing. That is, Vr dot is positive. If you consider at any quadrant, you can see that Vr dot is positive if you mark a direction as shown in this figure. Similarly, you may be able to see that for these two quadrants, that is here V theta is negative and Vr is positive. One is positive, other is negative. Therefore, V theta dot is positive. That also can be observed from here. So here in these two quadrants, it is positive. V theta dot is positive, and in these two quadrants, V theta dot is negative. Therefore, the V theta Vr trajectory will be like this one. That is, it is moving from here and goes to this point. Similarly, moving this way and goes to like one. That is, suppose the point is here, then it cannot go this way or it cannot go this way. It is not possible. But from here, it can go. Okay. That is when V theta is equal to 0, both VR dot and V theta dot are 0. V theta is equal to 0. So you substitute here V theta is equal to 0, then VR dot is equal to 0, V theta dot is equal to 0. That is, once V theta is equal to 0 or theta dot is equal to 0, then it is a stationary point. That is, after that, as time increases, the trajectory will not change, or the values of VR and V theta will not be changing. Thus, the points A1 and A2 are stationary points. This point and these points are stationary points for which V theta is equal to 0, and so this derivative and this derivative is 0, which is constant. VR and V theta will be constant. Now we will see three different cases based on these discussions. Okay, I will show you one by one. First case, this one. This is called a collision triangle. Initially, let missile is here and target is here. Missile is moving along this direction and target is moving along this direction. At t equal to 0, this is the position. At t equal to t1, this is the position of the missile and this is the position of the target. And the LOS angle is angle of, this is the LOS, and angle with respect to x-axis, reference axis, that is theta. But this is the case for t equal to t2 and this is the case for t equal to t3. But you can see that in all these cases, theta is same. There is no change in theta. If that condition is satisfied, then theta dot will be 0. That is, it is a stationary point. Theta dot equal to 0. Then one more thing you can see that as the engagement proceed, the distance between missile and target is decreasing. Distance between missile and target is decreasing, and finally they will collide at this point. Therefore, from here we have got a very interesting result that in order to guarantee that a collision is possible or collision is achieved, then the theta should not change. Theta dot should be 0 or theta should be a constant. Also, the distance between missile and target should decrease as the engagement proceeds. Therefore, the conditions are theta dot is equal to 0 and r dot is less than 0, or v theta is equal to 0 and vr less than 0. But these are the conditions that must be satisfied in order to achieve a collision between missile and target. Now, here this is another case where we can see that the values of theta are not same here. They are different here. And you can see that here, even though the values of theta seems to be increasing, but it is increasing the negative direction. Therefore, actually, theta is decreasing. Therefore, theta dot will be negative in this case. Anyway, theta dot is not 0. And also this distance between the target and missile is decreasing. That condition is satisfied, but the other condition, theta dot equals 0, that condition is not satisfied. And finally, you can see that no interception is possible, because at this point the missile is here, target is here only. Therefore, the interception is not possible. After some time, missile will go here and target will come this way. Therefore, this collision is not possible in this case, because here the first condition, theta dot equals 0, that condition is not satisfied. Therefore, no collision. The third case, here you can see that theta is same throughout. That is, theta dot equals 0. First condition is satisfied. But this is the initial case. This is t equal to t1, t equal to t2, t equal to t3, etc. Therefore, here we can see that the distance between missile and target is increasing as the engagement proceeds, and we can see that here it is not possible to have an interception. Therefore, what we can conclude is that the condition for a guaranteed collision between the two is that theta dot should be equal to 0 and r dot should be less than 0. If these two conditions are satisfied, then definitely a collision will be achieved. If theta dot equals 0 and if r dot is greater than 0, then no collision is possible. In that case, the avoidance, if the avoidance is our objective, then this condition can be used. Now we can consider an initial engagement between missile and target as shown given by this data. And for this, missile velocity and target velocities are given. And here, the relative velocities are also found. We can see that if you do this one, the VR will be negative and V theta will be equal to 0. The both conditions are satisfied. Therefore, in this case, a collision is possible, and for all other initial conditions, a collision is not possible. Therefore, only for this particular initial condition, the collision is possible, provided you are not giving any guidance law. Therefore, what we are going to do is that we will apply a guidance law such that these two conditions are finally satisfied. Once it is satisfied, then a collision will be possible. Now we will discuss some guidance laws. One is proportional navigation guidance law. It is also known as PN guidance law. This is one of the most widely used guidance law because this guidance law is very simple and easy to implement, and it is robust. Now we can see how this PN guidance law is developed, or what is the history behind it, the development of this guidance law. Earlier, now we know that the mariners are using some sophisticated instruments, but in earlier days it was not so. Therefore, what is the thumb rule that the mariners were using to avoid a collision with another ships? So there may be a number of ships, and each of the ship should make sure that that ship is not colliding with any other ships. The thumb rule that they have used is, when a neighboring ship appears to be stationary and seems to be growing in size, a collision is imminent. That is, if we feel that if the people in a particular ship feel that the other ship is stationary, and also they feel that the size of the other ship is growing, then surely a collision will be there. But that is the analysis that we can have. That is, the other ship appears to be stationary with our ship implies that the line of sight between two ships is stationary. That is, the line of sight is not changing. That is the meaning. If it seems to be stationary, if the other ship seems to be stationary, it means that the line of sight between our ship and other ship is constant. It is not changing. That is, theta is not changing. V theta is equal to 0. And the second condition, that is, the size of the other ship seems to be growing in size, it implies that the LOS separation between the two is decreasing. That is, VR is less than 0. Actually, they were using these two conditions. That is, V theta should be equal to 0 and VR should be less than 0. If these two conditions are satisfied, then they know that a collision is sure, and therefore they have to maneuver such a way that a collision is avoided. Actually, these are the two conditions which are necessary and sufficient to ensure that an interception of the missile with the target is possible. But these two observations were used in designing the proportional navigation guidance law. The second observation, that is VR less than 0, can be achieved if the missile is launched approximately towards the target or predicted collision point. If it is moving, then we have to see what is the predicted collision point, and the missile should be pointed towards that point. If it is stationary, then the missile should be pointed towards the target point. The first observation, that is V theta is equal to 0, but that condition can be satisfied if the missile turn rate is made proportional to LOS rate. That is, while vehicle is moving like this one, then the missile has to be turned. But that turn rate, that should be proportional to LOS turn rate. That is theta dot. So gamma m dot is equal to theta dot. If that condition is satisfied, then the second condition can be achieved. But therefore, we can write the guidance law as gamma m dot, that is the missile turn rate, that is proportional to LOS turn rate to theta dot, or gamma m dot is equal to n theta dot. This n is known as navigation constant or PN constant, etc. Therefore, the lateral acceleration will be equal to this turn rate, angle turn rate multiplied by velocity, that is nvm theta dot. But this is the guidance command that is applied to ensure that a collision between a target and missile is possible. But this is known as PN guidance law. I will show some simulations. So we can assume that we have a missile target engagement with these initial conditions. That is, initially the missile velocity vector is at 60 degree. Also, the target velocity vector is at 45 degree. Initial LOS angle is 30 degree. Initial separation between the two is 7,000 meter. Also, we assume that the target velocity is 250 meters per second and the missile velocity is 400 meters per second. Also, one more assumption, the target is non-maneuvering. If you do the simulation by using this PN guidance law and by using the mathematical modeling that I have explained, r dot, theta dot, and gamma m dot, then you can see you will be getting a trajectory like this one. This red is the trajectory of the missile, and this one is the trajectory of the target. And we can see that both are hitting at this point. As collision is achieved. And this is the graph showing the variation of the range, that is LOS separation and the time. You can see that at t equal to nearly 45 seconds, the distance between the two is 0. If the distance between the separation between the missile and target is 0, means a collision is achieved. Now we will consider the case of maneuvering target. Suppose the target is maneuvering. You can see that the target is moving like this one. And in that case also, the missile is able to achieve a collision with the target. So this is a variation of the range with respect to time. And we can see that equal to 25 seconds, the LOS separation is 0, meaning that a collision is possible. So by using a PN guidance law, we can achieve a collision between a target and the missile. And there are a number of guidance law. I am not going to discuss all these guidance law. If you are interested, you can go to literature and see different types of guidance laws. Okay. Now we will see impact angle guidance law. That is, impact angle means the angle at which finally the missile hits the target. It can be 90 degree, or it can be 30 degree, or it can be 40 degree, etc. Okay, see here. But suppose this is a target, but we can hit like this one. In this case, if this is a reference, the angle is 90 degree. Therefore, theta f is equal to 90 degree. Or we can hit the target like this one. In this case, theta f is equal to 0. Or we can hit the target like this one. Then this is the theta f, maybe minus 30. And you may know that the direction at which the missile is hitting a target is very important for destroying that target. But depending upon which direction, if you hit in along a particular direction, then the disaster will be more. But therefore, the final angle is important to achieve a more effective collision of the missile with the target or to destroy the target. Now, how we can achieve this desired impact angle? But that is the next discussion. But here we have a target. We assume that the target is stationary. Even if it is maneuvering, then we can find the predicted interception point, and that point can be considered as our goal point, and that point is stationary. Okay. Now, as I explained earlier, this is the LOS separation, and that distance is denoted by the letter R. This is the LOS angle theta. This is the flight path angle gamma, and this is sigma. Sigma is the angle between this flight path angle and the LOS angle, or gamma minus theta is sigma. It is also known as heading error. And this is the lateral acceleration. Lateral acceleration means this acceleration that is applied perpendicular to the velocity vector. Therefore, if you apply an acceleration, lateral acceleration, then this velocity vector will be turned so that we see that it will move along particular curved paths. Okay. Therefore, the sigma, that is heading error, is defined as gamma minus theta. Our objective is that the target should be collided by the missile with a desired impact angle. Suppose it is hitting like this one, then this angle is theta f, that is final angle. That should equal to gamma f. Okay. Finally, theta f and gamma f will be equal because at final interception point, sigma is 0 because they are colliding along that LOS direction. Then only collision is possible. But sigma f will be 0. Final sigma will be 0. If you put sigma is equal to 0, sigma f equal to 0, then you can see that gamma f minus theta f equal to 0. Therefore, gamma f is equal to theta f. Finally, this gamma f will be equal to theta f. Now, the state space model of the kinematic equation can be obtained like this one. Okay. Because here the component of this velocity along this LOS direction will be v cos sigma. Actually, it is v cos gamma minus theta, but gamma minus theta is defined as sigma. Therefore, this velocity will be v sigma. And target is stationary. Therefore, this velocity will be 0. Therefore, the relative velocity along this direction will be 0 minus v cos gamma m. Sorry, v cos sigma. Therefore, that is equal to minus v cos sigma. Or we will be getting r dot is equal to minus v cos sigma. Similarly, r theta dot is equal to minus v sin sigma. Why? Because here also the velocity here, target velocity is 0 because it is stationary, and the component of this velocity along the direction perpendicular to LOS will be equal to v sin sigma. Therefore, we will be getting minus v sin sigma is equal to r theta dot, or theta dot is equal to minus v sin sigma by r, and gamma dot is equal to n theta dot. That is the guidance law. That is, we are applying the Pn guidance law. If you are applying the Pn guidance law, this will be gamma dot is equal to n theta dot, and this expression, equation number 20, will be changing with respect to the guidance law that we are using. But these two are the basic kinematics. That is constant, that is fixed. But this is the controlling factor. By changing this gamma or gamma dot, we are controlling the flight path. Therefore, this will be changing. Therefore, different researchers will be using different guidance laws, and accordingly, this gamma dot expression will be changing. Since we are using Pn guidance law, we have written gamma dot is equal to n theta dot. Now, in order to achieve a desired final angle, we need a relationship between final impact angle and the navigation constant n. If you get such a relation, then you can vary or you can compute the value of n, and you can use the value of n is equal to that particular value. But that is the idea that is being used here. For that, we can integrate. Before that, we can do something. That is, we know sigma heading error is equal to gamma minus theta, or sigma dot is equal to gamma dot minus theta dot. And for Pn guidance law, gamma dot is equal to n theta dot minus theta dot. But that is equal to n minus 1 theta dot. But sigma dot is equal to n minus 1 theta dot. Because this is easy to integrate. Now we can integrate. If you integrate this one, you will be getting sigma f minus sigma 0 in the left side, and here we'll be getting n minus 1 into theta f minus theta 0. And we have already explained that sigma f should be 0. At the time of interception, there is no heading error. For sigma f equals 0, 0 minus sigma 0 is equal to n minus 1 into theta f minus theta 0. And also we have seen that theta f is equal to gamma f. Therefore, you can substitute gamma f here. And so by substituting theta f is equal to gamma f here and sigma f is equal to 0, you will be getting an expression for gamma f. You will be getting an expression like this one: gamma f is equal to theta 0 minus sigma 0 by n minus 1. Now, our objective is that we should get a value, we should be able to compute the value of navigation constant such that it is a function of the desired final angle, and also, of course, it is a function of the initial conditions. Now, if you rearrange this equation, then you will be getting an expression for theta. Okay. So, that will be equal to you will be getting like this one: n is equal to 1 plus okay. I will explain how I got this one. Theta for gamma f. What I have done here is that actually this is expression that we have got. Now, if you use this expression, surely you will be able to achieve the desired impact angle. But the problem is that if there is some disturbances or some other issues, then you may not be able to achieve the desired impact angle. In that case, we have to do a feedback control. That is, at each instant, we have to compute the navigation constant such that the present value, the current value of theta and sigma are assumed to be the initial values of theta and sigma, and gamma f, of course, the desired final angle. If you do so, then you can write gamma f is equal to theta minus sigma by n minus 1. Actually, this expression is obtained from this expression. But this expression can be used for the ideal scenario where there is no disturbances, no other issues, no autopilot and lag, etc. If that is the case, then we can use this guidance, this expression. Otherwise, we have to compute the navigation constant at each instant. If so, if we are doing so, then this theta 0 will be changed to theta and sigma 0 will be changed to sigma. But this is the navigation constant if you are using the feedback control. And our guidance law is nv theta dot, where n is computed using this equation. Therefore, if you use this equation and you are finding n, then you will be able to achieve the desired impact angle. Okay. So we can see a simulation result. So here, the initial flight path angle is assumed to be 90 degree. Initial LOS angle is 30 degree. And initial separation, LOS separation is 7,000 meter. Also, vehicle speed is 400 meter per second. We are considering two cases. In the first case, we are interested to achieve an angle 15 degree at the interception time, or impact angle is 15 degree. And for the second case, we are interested to achieve gamma f2 is equal to 0 degree. And I have done the simulation, and you can see that initially it is at 90 degree. That is why missile is going like this one, and it is maneuvering, and finally it reaches the target point. And here you can see that if you extend this like this one, and if you draw an horizontal, then this angle will be equal to 15 degree. That is the desired of impact angle is satisfied here. And for the second case, our objective is that the desired final angle should be equal to 0 degree. It is very obvious that it is achieving 0 degree at the interception time. It is a 0 degree. Therefore, by using this methodology, we can achieve a desired impact angle. What strategy we have used is, our guidance law is NVM theta dot, NV theta dot, where the value of n is computed such that uh, we we are achieving a desired impact angle. For that, we should have a relationship between n and sigma f. Of course, a relationship between this sigma f also on the initial conditions. But that formula we have obtained here. Therefore, if you compute n using this formula, so this sigma 0, you know, theta 0, you know, gamma is our desired impact, final impact angle. Now, substituting these values here, you will be getting the value of n. And if you use that n here, you will be able to achieve the desired impact angle. But there is some issues. Now, if you are using PN guidance law, then there is a condition that n should be greater than or equal to 2. Otherwise, your final acceleration will be infinity. I am not going to have a discussion on that, but this result you may note, that is n must be greater than or equal to 2. So therefore, if you substitute n is equal to 2 here, then this will be theta 0 minus sigma 0. But that is the minimum possible final impact time. The final impact time, that minimum possible value is theta 0 minus sigma 0. And in order to get the maximum value, this n should be equal to infinity. If it is infinity, sigma 0 by infinity is 0, gamma is equal to theta 0. But this value is an ideal value only, because if n is infinity, then our lateral acceleration will be n with theta dot, that will be infinity, which is not practically feasible. Therefore, ideal case, we can have impact angle up to theta 0. Therefore, if you use this methodology, then the final desired angle should be between theta 0 and theta 0 minus sigma 0. For example, theta 0 0 and sigma 0 30, and if it is so, then it should be between 0 and minus 30. In that case, you cannot have a 90-degree interception at the interception angle at the final stage. Therefore, there is some limitations if you use this methodology, and there are so many papers in literature that you can see that they were able to achieve the full 360-degree impact angle. That is, you can have any desired impact angle is possible. Some guidance laws were developed. You can go to, you can see some papers in the literature. And finally, we will discuss guidance laws for impact time control. Now, as I explained earlier, the primary objective is that the missile should hit the target. But besides this main goal, there are some other constraints. For example, impact angle constraint that we have seen. And also, there is a constraint on the time at which the missile hits the target. For example, suppose I say that my missile should hit the target at t equal to 20 seconds. But there is a constraint. It cannot be 21 seconds, it cannot be 90 seconds. It should reach there exactly at 20 seconds. Why so? I will explain. Now, suppose a missile of enemy nation, enemy country, is coming to attack our country. Then we should destroy that ship. For that, we may launch a missile to destroy that missile. But that ship is having some self-defense mechanism. It is known as closed-in weapon system, CIWS. So by using this mechanism, this ship is able to destroy the missile that we have launched. Therefore, our objective is not satisfied. We have failed to achieve our goal. But if you launch a number of missiles, for example, suppose I launch 4 missiles, And if all of these missiles reach the target simultaneously, then that missile may be able to destroy one or two missiles, and then the other missiles will be able to destroy the enemy ship. Therefore, the impact time control is important in that aspect. That is impact time means the final time, that the time at which it hits the target, that should be controlled. Also, in the case of unmanned aerial vehicles, there are some applications. For example, suppose some specific regions of surveillance, if it requires a lot of resources simultaneously, for example, flood monitoring and fire control. In such conditions, it may be required to arrive a number of UAVs at their waypoints simultaneously. In that case also, we have to develop a guidance law such that the final time is controlled. But there are so many methods. One method is that we will control each of the missiles individually such that they are all are commanded with a common impact time. For example, suppose I have 4 missiles and I am commanding my desired impact time as 30 seconds for all the missiles, and I am applying this guidance strategy. Then each of these missiles will move by using the guidance command that is applied to it, and all of them will reach the target point at t equal to 30 seconds, and they will succeed in their mission. But that methodology is used in this explanation. Now, what is our problem? So we have a missile and we have a target. This is a target point. We assume that the target is stationary so that our kinematic model can be simplified. But this is an instantaneous position of the missile. But this is the, as defined earlier, R, theta, gamma, V, AM, everything we have defined earlier. The same point. This is the initial launch point. And these kinematic equations, that is same as that we have obtained earlier. And this gamma dot is equal to AM by V. The objective is that we have to develop a formula for AM so that it will satisfy two conditions. That is, one, it will hit the target. Second, it will hit the target at a desired predefined impact time. The objective is to find prosperity guidance law governing AM, which can guarantee a desired impact time TF. And by using this guidance law, we should be able to have a simultaneous impact of multiple missiles at that predefined impact time TF. That is our objective here. Now, basic strategy. Now, this is the missile point and this is the target point. The missile can move along this path P1, or it can move along P2, or it can move along P3, depending upon the gamma dot or the angle turn rate that we have applied. If it is moving along this path P1, then we can see that the path length is smaller. That is, path length of P1 is small as compared to that of P2. It is small as compared to P3. Now, if the velocity of the missile is constant throughout, or if we consider the average velocity, then we can see that a missile which is moving along this path will have maximum impact time, and a missile moving along this path will have minimum impact time. Therefore, in order to get different impact times, what we have to do is we can vary the path lengths. Now, how we can vary the path length? Path lengths can be varied by varying the turn rate gamma dot, and gamma dot can be varied by varying the lateral acceleration AM. Therefore, our objective is that we can find an expression for AM so that a desired gamma dot is obtained, and thereby we will be able to achieve the desired impact time. Okay. Now, first we can go for PN guidance law. The PN guidance law, the guidance command is A is equal to NV theta dot. Now, for the parameter that we can vary theta dot is by varying N. As we have done for the case of impact angle, we should be able to get an expression for N, which is a function of the desired impact time. Then we will be able to control the final arrival time of the missile. But we can see whether it is possible or not. But this is a PN impact time. You can calculate the expression for the impact time using the PN guidance law. For this, we have already seen these equations. But this is the heading error gamma minus theta. Actually, we want to control gamma dot. But gamma dot can be controlled by controlling gamma sigma dot or theta dot. But theta dot we cannot control. It is a kinematic equation. Therefore, the only thing is that we can control sigma dot. By controlling sigma dot, we will be able to control gamma dot, and thereby we will be able to control the turn rate, and thereby we will be able to get the different path lengths, and so that different types of impact times can be achieved. But this I have already explained how this expression is obtained. This one, sigma dot is equal to n minus 1 theta dot. And substitute this theta dot, that's minus v sine sigma by r here. We will be getting an expression for sigma dot. And here we can see that sigma dot, it is a function of sigma as well as r. That is it is a coupled equation. Also, it is a nonlinear equation. But this is a coupled nonlinear equation, and integration of this equation is very difficult to get. Now we can obtain the integration, or we can integrate sigma dot, provided you could find an expression for r in terms of sigma. If you are able to find an expression for r in terms of sigma, then this equation will be an expression of sigma only. Then there may be a chance for integrating this expression, and once you are able to integrate, you will be able to get an expression for the final time. For that, what we are doing is that we will divide this equation by this equation. This is dr by dt, this d sigma by dt. If you divide this equation by this equation, you will be getting dr by d sigma, and here minus v and minus v will be cancelled. Cos theta by sin theta, and 1 by r will be there. So you will be getting an expression like this one. And you take r to this side, that is variable separable. But dr by r is equal to 1 by n minus 1 d sigma by tan sigma. But therefore, in the right hand side, it contains only sigma, and the left hand side, it contains only r. If you integrate this one, then you will get a closed form expression for r. R is equal to k sine sigma all raised to 1 by n minus 1. Here, this k can be found by substituting the initial conditions in this expression, and you will be getting an expression for k like this one. So here you can see that the expression for r is a function of sigma alone. Therefore, if you substitute here in this expression, then you can see that equation 39 will contain only terms with sigma. That is being done here, and we have got an expression for sigma dot is equal to minus n minus 1 v by k sine sigma all raised to n minus 2 by n minus 1. Therefore, dt is equal to, this is d sigma by dt. Therefore, if you do variable separable, then you will be getting an expression for dt like this one. And if you can integrate this one, that is, if you can integrate this expression, then this will be tf minus 0. If you integrate from 0 to tf, this will be tf minus 0 equal tf. That we can integrate. And this side, these are constants. And if you are able to integrate this expression, then you have succeeded to get an expression for tf. But this is not integrable, because this is non-elementary antiderivatives, and it cannot be integrated, and therefore it is not possible to get an exact closed form expression for the impact time using the PN guidance law. This is issue. If you are able to integrate this one, then okay, you will be able to do it. Now, how we can compute the impact time using the PN guidance law. One is numerical integration. That is, of course, possible by using some simulation softwares like MATLAB. You will be able to integrate this one numerically, and you will be able to find the expression for impact time. But the thing is that in that case, you will not be getting an expression for n as a function of the desired impact time, just like we have obtained here. Here we have obtained expression for n as a function of the desired this impact angle, but such thing is not possible if you find the impact time by using the numerical integration. The other method is we can approximate using Taylor series. That is, this sine sigma all raised to 2 minus n by n minus 1 can be approximated, and we will be getting a polynomial, an infinite polynomial. A polynomial is easily integrable, therefore we can integrate. But the thing is that that is approximate only. In that case also, even though you are able to find an approximate expression for TF, you are not able to get an expression for navigation gain, that is a control parameter, as a function of the desired impact time. Therefore, that is an issue, that is a challenge, how we can solve that issue. Here you can see so many papers that uses impact time control. One method that they are using is they will change the navigation gain indirectly, because there is no direct relation between this n and TF. Therefore, indirectly they will change the navigation gain n. That is, they will add a factor k into TF minus TD to n. But TF will be computed by using either of this method, and they will find the error TF minus TD, and it will be multiplied by some proportional constant, and that will be added to n. And finally, when we are getting a particular value of n, then this TF will be equal to TD. Therefore, this term will be 0, n will be constant, and our objective will be satisfied. That is one method. Another method is that we are not changing the value of n. Instead of that, we are adding one more term to the guidance command. That is, we are adding a command k into TF minus TD to the guidance command, not to the navigation constant. But these are some approximate method, and it requires either numerical integration or approximation using Taylor series expression, and also we are not able to get an expression for the control parameter n. And recently, I have seen a paper where they have integrated this expression using incomplete beta function. But that is also a numerical method. But there, the achievement is that they are able to get the impact time exactly. An exact expression for the impact time is possible if this is integrated using incomplete beta function. But there also the issue is that there is no expression for the navigation gain, which is the control parameter, as a function of the desired impact time. Therefore, the issue is still there. Then how we can solve this issue? Okay. Our research problem is that can we formulate a guidance law such that an exact closed form solution for the impact time is possible? Also, the impact time can be controlled by a parameter which is an exact closed form expression in terms of the desired impact time. But these are the research problem. Actually, this is the research problem that is addressed to me. Fortunately, or for my lucky, I was able to solve this problem, and I will explain how this problem is solved. Okay. Now I will explain the control formulation. I assume that my initial heading error is between this range, minus pi by 2 and plus pi by 2. That is my assumption. And I am proposing a two-phase variation in the heading error sigma as a function of the range R, as shown by equation 46 and 47. But there are two phases. In first phase, the heading error varies according to this expression. And in the second phase, the heading error will be 0. That is, this is up to FR0. If your range, initially the range is R0, the range is decreasing. And when the range reaches FR0, where the value of F is between 0 and 1, it is a fraction. Suppose F is equal to 0.8 and R0 is equal to 10,000, 0.8 into 10,000, that is 8,000. If the value of r reaches 8,000, then this will be 0. Then after that, the heading error is 0 throughout. But this is the, I assume that I want a variation in the heading error which satisfy this equation. Why I have chosen this equation, that we can see later, that if I choose an equation, if a heading error variation as given by these two equations, then I'll be able to integrate expression for impact time. But that is the objective. Therefore, that is, I am proposing a function that is a variation for a function which is the variation for the heading error, such that that function is integrable. Also, it should be 0. The heading error should be 0 at the time of intersection, and the r should be 0 at the time of intersection. These two conditions must be satisfied. Otherwise, no intersection will be possible. But this is a proposed variation of the heading error. But this is my initial heading error. By using that method, the heading error will vary like this one, and it will reach 0 at this point. After that, it will be maintained 0. But there are two phases. In first phase, the impact time is, engagement time is Tc, and for the second phase, the engagement time is Tf minus Tc, and Tf is the desired impact time. But at that time, the range should be 0. Otherwise, no collision is achieved. At this time, r is equal to fr0, where f is between 0 and 1. Now, we can differentiate equation 46 with respect to time. In order to find the impact time Tc, first we are differentiating this one. If you differentiate this one, this will be cos sigma dot is equal to, you will be getting an expression e raised to minus b r by r0 minus f into r minus b by r0 into r dot. If you differentiate this equation, you will be getting this expression. And finally, from there, this r dot is actually minus v cos sigma. That is from the kinematics. We know that r dot is equal to minus v cos sigma, and therefore cos sigma and cos sigma are cancelled. But that is also a consideration in developing that formula, because I want to cancel this cos sigma. Otherwise, there will be r dot minus v cos sigma, then integration may be difficult. R dot is minus v cos sigma, therefore I want a cos sigma in the differential form. But that is one of the reason for choosing sine sigma there. You can see sine sigma here. Therefore, if I differentiate this one, cos sigma will be coming. And if I differentiate, r dot will be coming. R dot is equal to minus v cos sigma. Therefore, this r dot will be cancelled. That is, this cos sigma and this cos sigma will be cancelled. But there will be a minus v, and that minus v and b minus bv by r0 into e raised to minus b r by r0 minus f. I want this expression in as a function of sine, sigma, because I got sigma dot, then only I can integrate it. Now that also can be obtained from here. E raised to minus b r by r0 minus f is equal to 1 minus sine sigma. That can be obtained from here. But that substitution also done. Then I have got an expression for sigma dot like this one. For the time being, we can assume that sigma is positive. Therefore, this sine sigma need not be considered. Therefore, we will be getting minus bv by r0, 1 minus sine sigma. And gamma dot, we know it is sigma dot plus theta dot. Therefore, you add sigma dot plus theta dot is from the kinematic equation we got. If you add these two, we will be getting gamma dot, and multiply this gamma dot by v, then you will be getting am. But this is the guidance law. For guidance law, I have got. But I should ensure that there is a control parameter which is a function of the desired impact time. For that, I should be able to obtain a closed form expression for the impact time as a function of the parameter. Here you can see two parameters are here, b and f. This b can be obtained by substituting the initial condition. So that will be log 1 minus sine sigma 0 by f minus 1. So b is a function of the initial condition and the parameter f. And f is actually the control parameter. So f is the control parameter. B is a parameter which is a function of the initial condition as well as the control parameter. This b satisfies the initial conditions. Now we can derive expression for impact time. Um, but this was our expression d sigma by dt is equal to this expression. Therefore, I can take the terms contain sigma to this side and dt to this side. Then we will be getting an expression like this: minus v dt is equal to r0 by b into sine sigma by 1 minus sine sigma d sigma. Now this is easily integrable, minus v into integral 0 to tc, because uh, at r equal to fr0, the time is tc only. So 0 to tc dt, that is equal to r0 by b, sigma 0 to 0. Initially the heading is sigma 0, and finally at that at the final stage of the initial phase, sigma is equal to 0. Well, the sigma variation is from 0, sigma 0 to 0, and this is expression. Now you can see that this expression d sigma by 1 minus sine sigma is easily integrable, and the integral is this one: 1 minus tan sigma 0 minus 6 sigma 0 divided by v. That is, we have got a closed form expression for tc. That is, for the first phase we have got a closed form expression. That is, for this one we have got this expression tc we have got. Now we can find the expression for impact time for this one, that's tf minus tc. Phase 2. And phase 2, the heading error is 0. Therefore, heading error 0 means it is moving along a straight line. There is no curved path. It is moving along a straight line. In that case, the time is just distance by velocity. But distance is f into r0, because at that time r is equal to fr0. The distance is fr0. Speed is v. Therefore, if you divide fr0 by v, you will be getting the time for the second phase. And the total time will be sum of these two times, and we will be getting an expression like this one, which is a closed form expression for the impact time. But here you can see that this expression contains the parameter f, and also it contains the expression for the desired impact time, and also it is a closed form expression, and it is a exact also. Therefore, now we have to find an expression for the control parameter as a function of the desired impact time. That we can obtain from here. Before going to that, I will find the maximum possible impact time and minimum possible impact time. For that, I should know how the impact time or the engagement time varies as a function of f. That is, as f increases, the minimum value of f is 0, maximum value of f is 1. Therefore, if the f is increasing from 0 to 1, how this impact time is varying, whether it is increasing or decreasing, remains the constant. In order to know that, we can take the derivative of this function with respect to f. That is, we can take dot tf by dou f, and from the sign of this one, we can see the variation. So I have taken the partial derivative tf with respect to f, and I have got an expression like this one, which is less than 0, negative. It means that as f increases, tf decreases. Therefore, the minimum value of tf is possible for maximum value of f, and maximum value of f is 1. Therefore, if you put f is equal to 1, you will be getting minimum impact time. F is equal to 1 means this will be 1 minus 1, 0. This will be f1 into r0, r0 by v. Therefore, the minimum impact time possible is r0 by v. And maximum is possible with the minimum f. Minimum f is 0. Therefore, if you put f is equal to 0 here, then this term will be 0, and this will be 1 minus 0 means 1 into this expression. That is the maximum impact time. Thus, we have got an expression for the minimum impact time and maximum impact time. Now, these two can be substituted in this expression. Therefore, this can be written as this actually tf max, and this is tf min. Therefore, this will be tf max into 1 minus f plus tf min into f. But that expression is written here. Therefore, we have got a simple expression for the impact time. Tf is equal to 1 minus f into tf max plus f into tf min, where tf max and tf min can be obtained by computing the by using these expressions. So we can find tf min and tf max. Therefore, from this we can get an expression for f. See, this expression is closed form. This expression is exact. Therefore, we have got an exact closed form expression for the control parameter f, which is a function of the desired impact time, and also initial condition, because tf max and tf min are functions of the initial conditions. Thus, I have achieved in developing a guidance law where we can have an exact expression for impact time, an exact closed form expression for this control parameter, and that control parameter is directly related to the desired impact time. Therefore, if your desired impact time is 30 seconds, you just put a TF is equal to 30 seconds here, and you compute F, and then substitute this F value in your guidance law. You will be able to achieve a collision exactly at TF is equal to 30 seconds. But the only constraint is that the TF that you are selecting should be between the TF max and TF min computed by the above two expressions. Therefore, the guidance law algorithm is first we can compute TF min and TF max using that equations, then get a set of permissible values of TF like this one. But TF min is not possible because it is an ideal condition only for the if you want to get it this one, then the lateral axis should be infinity. But any value greater than this TF min is possible, and TF max anyway is possible. It is closed bracket, and this is the open bracket. Now select a TF from S. Then find the control parameter of using that equation, and compute B using equation 48, and generate AM by substituting this F and B. And you will be able to achieve the collision with the exact impact time. Now, as I explained the case of impact angle problem, here also there can be disturbances, or there can be autopilot dynamics by which the achieved acceleration may not be same as the commanded acceleration. There will be some time lag. There will be some time lag between the achieved acceleration and the commanded acceleration. Therefore, our guidance law fails to achieve the desired impact time if you use this guidance law, the guidance law that we have obtained earlier. If you use this algorithm, then you will be failing to get the desired impact time and collision because of this autopilot dynamics. In that case, we have to do the feedback controller. That is, we have to compute F and B at each instant. And also we have to find TF max and TF min at each instant. And you can see that here the desired impact time is replaced by TF minus T, because suppose our desired time is 30 seconds, at T equal to 10 seconds, desired impact time is only 20 seconds, because we have already covered 10 seconds. That is why TF minus T is coming here. But by using this expression, you will be able to control the impact time even under the influence of disturbances or autopilot dynamics. Now we can see some simulations, but these are the initial engagement and velocity of the missile. The initial position of the missile is at 0, 0. Now, first we will find a TF min and TF max, but they have obtained us 25 and 30.0741 second, and we can choose a time in between these two. That is, from this set we can choose a time. I have taken 28.4 seconds as my desired impact time. And I have done the simulation. This is the trajectory, and here you can see the heading error variation as explained earlier. For the first phase, this is the first phase variation, and it reaches 0 at R is equal to FR0. F is computed, and FR0 is 2830. Exactly at 2830, it is becoming 0, and the intersection occurs at the desired impact time 28.4 seconds. But this is the lateral acceleration command, and this is the trajectory. That is, the guidance law is succeeded in reaching the target exactly 28.4 seconds. You can see this 28.4 seconds. Exactly 28.4 seconds, it is reaching the desired location. Now, this is a different impact times for identical launch condition. Here we are considering different times: 27, 28, 29, 30 seconds. All are chosen from the this set, and you can see that these are the different trajectories, and all are able to reach the target point at the desired impact times. Now, feedback control with autopilot delay. We assume that an autopilot delay of 2.2 seconds is there. In that case, also our guidance law is able to achieve the collision at exactly the desired impact time 28.4 seconds. But you can see that here the control parameters are varying. It is not constant, whereas in the ideal case, the control parameters are constant. B and F are constant there. But if you consider the feedback control, the control parameters are not constant. Now, salvo attack means we have to achieve a simultaneous attack of all missiles. Here, what we can do is that we can find the impact time set of each of these individual missiles, and then we can find an intersection set, and we can choose a desired impact time from this intersection set. This is an example. But these are the minimum and maximum impact times for the missile 1, 2, and 3. And from this, we have to consider the intersection set. Therefore, the maximum value 26.7, here minimum value is 31.84. Between these two, we have to select an impact time. And you can see that all the missiles are able to reach the target point at exactly the same time. I have to consider two cases. One is 28.5 is the commanded time for all the missiles, but that is the trajectory for this dash trajectory is corresponding to 28.5 seconds, and this solid trajectory corresponds to TF is equal to 31 seconds. You can see even though initial ranges are different, finally all the missiles reach and the range is 0 at t equal to 31 seconds, which implies that all the missiles attack the target exactly at 31 seconds. If it is commanded so, if it is commanded 28.5 seconds, then all will reach here at 28.5 seconds. Okay, this is another way of achieving the simultaneous attack. Here we are not launching all the missiles at the same time. They are launching at different instance of time, maybe from the same location. But suppose missile 1 is launched at t equal 0 second, missile 2 at t equal to 1 second, missile 3 at t equal 3 second. Then suppose the desired impact time is 30 second. Then for the first missile, the impact time that should be commanded is 30 minus 0, 30 second. But for the second missile, it should be 30 minus 1, 29 second. For the third missile, it should be 30 minus 3, that is 30 minus 2, 28 second. If the missiles are commanded with these impact times, then they will be able to achieve the desired impact time. That you can see here. We want 36 seconds. That is, all the missiles should reach at the destination point at 36 seconds. But they are launched at 0 second, 2 second, 4 second, 6 second. Therefore, for this engagement time is 36. For this, it is 34 seconds is an engagement time because it is launched at 2 seconds. 34 plus 2 is 36. Similarly, you can see here also. But this you can see, all are launched from the same location at a gap of 2 seconds, but all are reaching at the target location at the same time. So here, even though they are launched at 0 second, 2 second, 4 second, 6 second, all are achieving 0 LOI separation at 36 seconds, implying that a simultaneous attack of the multiple missiles is achieved. But these are some references. Okay. If you are in doubt, you are free to ask me. If no
Hello,
doubt,
sir.
yeah, Srija.
Yes, sir. Yeah. My doubt is, if the target is a maneuvering one, so how do we incorporate all those complexities into this impact time and impact angle guidance laws?
Okay, but that is a real challenging problem. If the target is maneuvering, then one method that we can do is, I think nobody has solved that problem. But if it is maneuvering, then if it is possible to find the possible to predict the interception point. If that is possible, then we can consider that intersection point as the stationary target, and we can apply the same guidance law that we have developed here. Otherwise, this guidance law, not only this guidance law, all the guidance law that were developed so far will fail. I haven't seen any method, any research work that can solve in the case where the target is maneuvering. Okay.
Okay, oh, okay, sir. And also, we have seen the importance of the closing velocity information also, right?
Hmm.
So, but in your presentation and in your equations, I couldn't see that, or why it is not important. The closing velocity information is not important in this particular case. Uh,
Okay, closing velocity means r dot,
yes.
final velocity. Okay, that we can compute. That is r dot is equal to minus v cos sigma, and sigma is equal to 0 at the time of interception. Therefore, r dot will be equal to minus v. The closing velocity in my case will be minus v. Anything more?
Okay. Nothing. Yeah. Thank you.
Okay, thank you. Okay, any other doubt? Yeah.
Hope all the queries are over.
One more thing I have to add, that is, I have expected that there may be one question. In all this development, I assumed that velocity is constant. But in a real scenario, the velocity is not constant. And we cannot control the velocity also. In the case of UAVs, we can control the velocity. But in the case of missiles, it is very difficult to control the velocity. In that case, what we will do? But that is also a challenging issue. But I have solved that problem. But unfortunately, I could not publish it. That is why I am not explaining here. That is also possible. Even the velocity is varying. We can have the desired impact time control. Okay, over to Dimna.
In this section, we are enlightened by a great presentation delivered by Dr. Salim sir. Sir, you have explained the navigation and control of missiles from its very basic concepts and provided us with a very good overview about the topic. Thank you, sir, for sharing your valuable knowledge and time with us. So,
Thank
on
you.
behalf of our Triple Department, GC Trishur, and all the participants, I extend our sincere gratitude towards you, sir. And thank you, participants. We will get back to you on tomorrow, 9:30 a.m. Thank you all.
Thank you. Thank you.